Hi, everybody. It's Ajanette, and I'm here to go through your Chapter 11 lecture for statistics, and that is covering your repeated measures t-test, which corresponds to a within subjects or a within group design. And so we also sometimes call that a paired sample t. Not only can it be used in a pre-test, post-test format, it can also be used for a matched design, which you'll learn more about in your research methods class. I'm just going to go ahead and share my screen with you so I can bring up the lecture. I will say that Zoom gets a little spotty, so bear with me if for whatever reason it's not able to kind of follow along with the lecture. So it just takes a little bit of processing time for the PowerPoint to come up. If it starts to be challenging and difficult and it starts to have communication challenges, then I'll just, instead of trying to share it in presentation format, I'll just share it with the slides open on the side. And that tends to function just a little bit better for us, okay? Okay, so Chapter 11 is looking at the related samples T, repeated measures T, paired samples T, okay? You see it referred to different ways. I want you to know that if you ever see it in a book or a research study described in any one of those methods, it's the same thing. What you have to look at is kind of design structure, and that tells you what t-test they're using. So anytime we're comparing a sample to a population, we're either using a z-score test and going through the steps of hypothesis testing, or we're using a single sample t. We use the z-score when we know the standard deviation, and we use a single sample t when we do not. In an independent measures t, we know that they are two separate samples, different people in each group, and they correspond to two separate populations with different people in each group. We call that a between subjects design. When you have a repeated measures design, you have within subjects, the same people are in both groups, okay? Either way, they have corresponding populations. Like if I did it, I'm gonna test you. Now I'm gonna look at your anxiety, I'm gonna give you a drug, and then I'm gonna test your anxiety again. Well, you have a corresponding population of people who have anxiety without the, or excuse me, people who haven't been drugged, and then people who have taken the drug. And we're looking to make inferences about those populations based on the samples, okay? So independent measures, again, covers a between subjects design, different people and different groups. So you're comparing two groups of individuals. Both groups are separate and distinct individuals, produces two separate and distinct sets of data, and we're focusing on mean differences. In a repeated measures, we're focusing on the differences between the means of the groups, okay? In a repeated measures or within subjects design, you have the same people in both groups being measured repeatedly, in this case twice because it's a t-test. And so you have the dependent variable that's measured two or more times. For a t-test, just two. Same people in every group, right? So it's the same group for every treatment condition. And what it does is it helps to control that potential risk that the results are due to the individual differences of the people rather than the treatment effect. Because it controls for that bias, we can have a smaller sample size with our within subjects design or repeated measures team, okay? Here's the visual that corresponds. When I'm talking about formally defining it, it's a paired sample t-test or repeated measures t-test. Is a research, it's used with a research design where the dependent variable is measured two or more times for each individual in a single sample. So it's one sample, two groups of measurements, okay? So the same people are participating in every single treatment condition. And what we're doing now is we're comparing means from measurement 1 to measurement 2. So we're comparing the differences in those scores, so what we call difference scores between the groups. Independent measures, we call those mean differences. This one we call them difference scores because we have a score for measurement 1 for each participant, a score for measurement 2 for each participant, and now we calculate the difference between those two scores, which is what we call difference scores. So we are focused on difference scores between those measurements in all of our formulas, okay? The advantages of this is because we know since the same people are in both groups, the difference between the two measurements is likely because of the treatment and not individual differences. So we need to use fewer people because we're controlling for that bias, okay? We can also use it for a matched subject design where, let's say, I want to look at the effects of sexual assault on anxiety levels, and I have a group of individuals who have been sexually assaulted. Then what I can do is I can, I did not know what their anxiety levels were before the assault. I only know after. So what I can do is compare them to a group that haven't been sexually assaulted. But I want to match them on certain variables to make sure that there's not something inherently different. So I want any variables that I think are critical to anxiety, I'm going to match them on. I know gender is critical to anxiety. Women historically, the research shows, have higher levels of anxiety. We're more likely to be diagnosed with anxiety than men. Now, there's all kinds of potential explanations for that, but that's what the research shows pretty consistently universally. And so what we want to do is we want to make sure that we're comparing them to another group of women and not just anybody. So we're going to match them based on gender. We're also going to match the number, like if I have 10 sexual assault survivors, I'm going to get 10 non-sexual assault survivors. They're women, so I'm going to get 10 women. They might be between the ages of 22 and 24, so I'm going to match them on age. I might want to also match them on ethnicity because that tends to be a related factor for anxiety as well. There's different ethnic variations in anxiety outcomes. And so let's say if I have two Caucasians in my sexual assault survivor group, I want to have 2 in my matched group. If I have 3 Hispanics, I want to have 3 Hispanics in my matched group. And let's say I have 5 African Americans, I want to have 5 African Americans. And I did it that way specifically because we also know that unfortunately sexual assault disproportionately impacts our women of color. So they are actually more likely to be assaulted than their Caucasian counterparts. That's not to say when you're just looking at the numbers that there aren't more white victims, because there potentially could be, but representative to their corresponding population, we definitely see that our women of color are disproportionately impacted. So that's why I kind of broke up the group that way. In any event, I want to make sure I have a matched sample that looks as much like my experimental sample as possible. So the more factors that I match them on, the more difficult it is to find a matched group to meet those demographics. But that being said, I can use a repeated measures design when I'm, or excuse me, a repeated measures t-test when I'm using a matched design, okay? Because it's still looking at trying to control for individual differences based on any other demographic variables. Okay? So our notation differs a little bit in that now instead of having 2 groups, we have 2 scores, right? So we have score 1 for participant X and score 2 for participant X. We'll have score 1 for participant Y and score 2 for participant Y. And then each participant will also have a different score, okay? So they'll always have, and I shouldn't say participant 1 or participant 2, this is just saying the score for the first measurement and the score for the second measurement, and then their different score. So we would use X as our symbol for our raw score. We have 2 X's. We have the raw score for first measurement, raw score for second measurement, and then our difference score, okay? Now, this isn't necessarily participant X, this is raw score, okay? It can be participant 1, 2, 3, 4, whatever, however you want to label them, okay? So we're looking at how much change occurs from measurement 1 to measurement 2. So what is the difference between measurement 2 and measurement 1? Did scores increase? Did they decrease, right? So our difference score is measurement 2 minus measurement 1 tells us what happened. Did they increase? Did they decrease? Did they go up? Did they go down? So it tells you the direction of the score, okay? The sample of different scores is what we start to plug into our hypothesis testing. And we're looking at a mean difference score for the entire sample. And this is what we call a mean difference score, okay? The mean of the different scores is the sum of all the differences divided by how many scores we have. And then we also have a population mean difference score. So this is for our sample, and then this represents the difference score for the corresponding population. And given that when we go through hypothesis testing, we base those notations on the population null, it will use this symbol in the null notation, okay? Again, it's freezing a little bit, so let's see. It's gonna let me change. I'm just gonna stop sharing. I'm gonna start sharing again. Yeah, it's not letting me change. So I'm gonna stop sharing. Escape out for just a second. Close that out. And then I'm gonna bring it back up and we'll just leave it kind of open on the side, okay? So bear with me just 1 second. So I'm gonna reopen it, find my spot. Okay, so I think this is where we were at. Let me share my screen. I think Zoom is really frustrated with me and tired of working. Okay, so here is where we left off. We were looking at symbol for our population mean difference that we will then plug into our hypothesis testing. Okay, so our goals now are to look at do the differences in those measurements or the scores, are they significantly different than what we would expect, or what we would expect to see if the treatment had no effect, okay? So we're examining how those differences matter. Did it create significant differences from measurement 1 to measurement 2, or didn't it? So with the null hypothesis, again, it's based on population data notation or notation. Why am I losing that word? Statistical notation. So here's our null hypothesis, and we would expect the differences to be 0. There are no different score. If the treatment didn't cause a change from measurement 1 to measurement 2, then the measurement would be exactly the same the second time you measure it as it was the first time you measure it, okay? And then I'm looking at, and so in other words, if I looked at your anxiety and then I gave you a drug and I looked at your anxiety again, if the drug had no effect and it was a null hypothesis, then the difference between measurement 1 and measurement 2 would be 0, okay? Of course, there's always some level of error, so we want to figure out if that difference is reasonable. Alternate hypothesis is it's not, okay? So when I look at my formulas now, they're all going to be based on, our mean differences. So our mean differences is the sum of all our different scores for each participant in the study divided by n. Our paired samples T formula is going to look at the differences between the mean and population divided by estimated standard error. My estimated standard error formula is going to change. So it's going to now be based on my variance divided by my n, which means I need to go back and remember how to calculate my variance, which is sum of squared divided by degrees of freedom. And I have a new formula for sum of square because my sum of squares is looking at my sum of my squared deviations for my different scores, not each of the participant scores. I now essentially am creating a sample of different scores that I'm looking at. And I'm calculating a mean, a standard deviation, and a variance for those different scores. And so my formula for sum of squares becomes the sum of the different scores for each participant divided by n, and that's squared divided by n, okay? My degrees of freedom, because I'm still working with the same group of people, is just n-1. It's only one sample with two different scores, two different groups of scores, but the participants are the same, okay? So this is now a good time to take a break, stretch a little bit, do a little bit of reading, go through your chapter learning checks until it brings you to the point where you're actually going to do the hypothesis testing. We're going to start by looking at hypothesis testing for a two-tailed test. We're going to go through all the same steps of hypothesis testing that we would for any other test. And so assuming you come back from break, I'll walk you through those. You're going to state your hypothesis and your alpha level, right? We're going to default to our 0.05 alpha level. Our hypothesis for a null is that those differences equal 0. Our alternate, they don't. They are not equal to 0. Our critical region, we're going to look up our degrees of freedom formula, use the t-distribution table for a 5% alpha level in a two-tailed test. What would those boundaries be based on our degrees of freedom? We also then have to compute our t-statistic. If I work backwards, first I have my t-statistic. It relies on my mean differences and my estimated standard error. So I'm going to be able to calculate that with the individual raw scores, but my estimated standard error, I need to plug in my new formula, which relies on variance, which relies on sum of squares, which relies on a new formula to account for the fact that I'm calculating my sum of squared deviations from my different scores. And then our mean difference is going to be calculated by totaling all of our different scores for each participant divided by n, okay? So I do need to know how to break down the formula and how to calculate each of the components in the larger formula. Then after I calculate my t, bigger t's are more likely to reject the null, smaller t's are more likely to fail to reject. So I make a decision, state my conclusion, and write out my results using the appropriate template, okay? So it's simple, go through the same steps, and then I have to choose my effect size, same thing. I can use a Cohen's d, an estimated Cohen's d based on sample size. I can use a percentage of variance accounted for, or an R-squared, or I can use confidence intervals. So my Cohen's d formula changes because I'm basing it on difference scores, not mean differences or not just means for one sample. And then my R-squared formula, as I mentioned, never changes. It's just taking our t-value and plugging that in. And then our confidence score, as usual, our confidence is going to be now based on our different scores, right? And it's looking at our different scores plus t times the estimated standard error, and then our mean difference minus t times the estimated standard error to get those filled goalposts, okay? That correspond to whatever percentage of confidence. And then let me take you through an example of how this all works. So this particular study is looking at a group of individuals. So we're calling them individuals A through I. And we are measuring their pain levels under two different circumstances. So the first measurement, we had them put their hand in ice cold water, kind of like you're digging for a beer at the bottom of the ice chest. And it starts to hurt after a while, right? And so we let them say neutral words like golly gee, just neutral words. And we had them hold their water or their hand in that water as long as they could. And they could only say neutral words to kind of cope and manage their pain. And then we looked at how many seconds could they hold their water or their hand in that cold water before the pain became unbearable and they pulled it out, okay? And so this was their pain tolerance rating. Then we had them do, we obviously have to let enough time pass so that their hand can go back to normal, back to normal temperature. Then have them do it again where they're swearing and see, does cussing relieve the sense of pain? So what happens to pain tolerance scores if I let you cuss as opposed to using a neutral word, okay? So when you're rating pain on a neutral word, your rating levels appeared to be higher than when I was rating your pain with cussing. So you had lower reported pain levels cussing than you did with the neutral. But is that significant? Did the difference between those different scores reach a threshold of significance? So we go through the steps, we take our data, and we plug it in. So calculate the degrees of freedom first, and we're going to use the N-1 formula because we have one group. Then we're going to go through the formula, and then we make a decision, or we plug it into SPSS, okay? So walking through, assuming this was our data set, P is less than 0.05%. Our null hypothesis is the difference scores would equal 0. Our alternate or different scores would not equal 0. Calculating out my degrees of freedom, I had 9 participants, so N-1 equals 8. If I look up a 0.05 two-tailed test, my critical boundaries are going to be plus or minus 2.306. So anything above 2.306 is going to be a significant difference, critical region. Anything below negative 2.306 is going to be in the critical region. Anything in between those two boundaries is not in the critical region. Then I'm going to compute my statistic. I'm going to start by calculating my mean difference scores. Then I'm going to go and calculate my sum of squared deviations for my difference scores. And then I'm going to calculate my variance. Then I'm going to calculate my estimated standard error. And then I'm going to calculate my T, okay? And I am literally just looking at my difference scores total up to negative 18. So negative 18 divided by my number of participants is 9, equals negative 2. I plug that, I plug our D squared scores in, right? So 68 is going to be the sum of our D squared, our difference scores squared, minus our sum of our D, which is negative 18 squared, divided by N, 9. So that comes out to 32. So I'm literally getting everything from here, right? Calculated my difference scores, calculated my squared difference scores, okay? Then I'm going to plug that sum of squared deviations value, 32, divided by 8 to get my variance. Then I'm going to plug that variance into the formula for our estimated standard error to get my estimated standard error. Then I'm going to plug that in to the denominator for my formula for the T. So the top of my T formula is going to look at my mean difference scores, which I got up here. So negative 2 minus, assuming a null hypothesis, I'm assuming the difference scores for the null is 0, divided by my estimated standard error. So negative 2 divided by 0.667 equals negative 3. It is beyond my boundary, which means it was significant, so I reject the null, okay? And there were significant differences in reported pain tolerance for individuals when they were swearing compared to when they were using neutral words, okay? Okay, let's go to our next one. I'm going to now look at the effect sizes, right? And I'm going to calculate effect sizes for the same data. And for my estimated standard error, or excuse me, my estimated D, I'm going to plug in my mean difference scores, which I calculated before. And I'm going to divide by my variance, which I calculated before. So this is saying the treatment effect had a magnitude of 1 standard deviation. So it reduced our scores by 1 full standard deviation. Okay. R-squared is looking at what percentage of the variance in the overall study is accounted for through my independent variable, in this case, cussing, right? And I take my t-value, plug it in, and I end up seeing that about 53% of the variance in the study is accounted for through my treatment effect. Remember, that's a pretty significant effect. That's a large effect, right? Or pretty significant magnitude, I should say, okay? My confidence interval, again, looking at a 95% confidence interval, so 1 minus your alpha level. And you're looking at your difference scores plus or equals your mean difference plus your t times your standard error and then minus. So I do it twice. So first I do it, I plug that number in that I calculated earlier, right? So I say -2 plus the t value that I use, which was a 2.306, times our variance, which I calculated on the previous slide, or excuse me, not variance, estimated standard error. And I get my one boundary, and then I do that again, but I now I'm gonna minus out this. So one way I plus it, one way I minus it, and I get my boundaries, okay? Okay. So now this is gonna take you through how do we report these results. And we report the results by using our statement of significance, our statistical evidence. We make sure we include our effect size in that, and then our statement of interpretation with our descriptive stats. And so that ends up being changing from a neutral word to a swear word did significantly impact perceived pain reduction or pain tolerance or pain levels, really is what it was. Our statistical evidence, it's a T parenthesis 8 equals 3, P is less than 0.05, two-tailed, R squared equals 0.529. I'm partial to R squared. In ANOVA, you see those commonly used. So I'm partial to R squared. Most people use confidence intervals. So your statistical evidence piece just changes a little bit based upon whatever effect size you want to use. But here's our confidence interval being reported. And then we would have our statement of interpretation changing to a swear word, reduce the perceived pain level by an average of M equals 20 points with SD equals 2. Or you can say individuals who are, when swearing, individuals had a reported pain level of blah, 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 compared to, or had a lower reported pain level compared to that when they were not swearing, okay? So you can say it a number of different ways, but essentially you're telling me, was it significant or not? You're telling me what the evidence was, and then you're telling me who was higher or lower, and what are your descriptive stats, okay? Again, factors that affect our t-test, our sample size, mean differences. The larger the mean differences, the bigger the t. Sample sizes, increase your sample size, you get to minimize your standard error, so larger t. Larger sample variance is like that static. It creates a larger standard error, so it's harder to find differences, so it's likely going to be a lower t, okay? And then some things that we have to consider, which is a disadvantage of this test. A lot of people are like, well, why don't we just use this measurement then? Because there's challenges. Like if you after putting your hand in that ice bucket once, you might build up a tolerance, like your nerves get tired a little bit. Maybe you build up a tolerance. So of course you're gonna have lower pain levels the second time because you built up a tolerance. So the effects of exposing you to the treatment already in the first measurement could carry over and affect your performance the second time. So what we try to do is we try to counterbalance, and how we could do that is we could say, okay, if we had 10 people, instead of having all 10 people do neutral words first and then cuss, we're gonna have 5 people do neutral words first and then cuss. and measure the different pain tolerances in each condition. And then the other 5 people, we're gonna first have them cuss, and then secondly, have them use neutral words. So we're counterbalancing the treatment. We're saying, okay, half the group can get treatment 1 first, then treatment 2, and then the other half can get treatment 2, then treatment 1. And if in fact it is a treatment, it's a timing effect, because being exposed to the treatment carried over, then you're going to, it's kind of going to balance each other out. They're going to counter each other in the measurements here by breaking it up that way. Okay, so you're trying to control for those carryover effects or those testing effects. We do in fact, let me see. Your book takes you through the one-tailed test. We talked about advantages of using this repeated measures, is you can use smaller sample sizes. It's great when you're looking at how things change over time, and it helps to control for that bias. The counterbalancing we just talked about. The assumptions, again, independent observations and looking at normal distributions, okay? And then just walking you through, when do we use an independent versus a repeated measure? It all goes down to, you know, looking at the group, know that they both have pros and cons. Is it different people in each group? That's an independent measures. The, you know, what's the pros and cons? You know, we get to control for time-related factors, but that's the advantage. Okay, let me go back. In independent measures design, we don't have to worry about carryover effects from treatment 1 impacting your performance on treatment 2. But a repeated measures design, I don't have to worry about individual differences between groups, but now I have the problem of carryover effects. And so they both have kind of pros and cons. Independent measures design is kind of more simple conceptually, because that's how we've learned about experiments almost the whole time we've learned about them. And you have different people in each group, so it's easier to conceive that one's a control versus experimental. Versus a repeated measures design, we don't conceptually think of it that way, but it can be experimental too, by the way, but not in the historical context of the way we've been taught. It has pre-test, post-test effects, but you can use smaller sample sizes. So they both have their pros and cons. You have to weigh those out as researchers. If you have limited access to participants, then a repeated measures design might make more sense. You know, within subjects design might make more sense, okay? But you have to make sure you're controlling for those negative disadvantages through like counterbalancing. So either way, we try to control for things. We try to control for individual differences by having an assumption of homogeneity of variance. We try to control for the challenges with testing effects through counterbalancing. So this whole balance between research design and statistical control matters, okay? Okay, so that's pretty much it. I hope you enjoy. We will definitely go through the calculations in class using SPSS together. Let me know if you have any questions. Bye.